Why can rubber be deformed so easily, while steel resists deformation much more strongly? This material property is described by Young's modulus. In this exercise, your task is to determine the dimension of Young's modulus. Take about 4 minutes and try to solve it yourself. Read the problem carefully and first try to solve it on your own. Then compare your solution with my step-by-step explanation. In the end, it is not only about choosing the correct answer. What really matters is understanding how to derive the dimensions systematically. Today, we are looking at a task about the dimension of a physical quantity, given as a quantity equation for the quantity E. It is E equals force divided by area divided by the relative change in length. We are asked to find the dimension of the quantity E. Before we start, let us briefly clarify the term dimension. A dimension describes which base quantities a physical quantity is made up of. These are, for example, mass, length, and time. We write these as m for mass, l for length, and t for time. So a dimension has the form m to the power of a, l to the power of b, t to the power of c, and so on. Now we proceed step by step. First, we look at the numerator of the equation. There we have force divided by area. Force divided by area is called mechanical stress. Depending on the type of load, we speak, for example, of tensile stress or compressive stress. What is important here is this. Young's modulus itself is not a stress. It is a measure of the stiffness of a material. Now let's look at the units. The unit of force is the Newton. The unit of area is the square meter. So force divided by area gives newtons per square meter. Now we look at the denominator of the equation. There we have delta L divided by L. That is a change in length divided by a length. Both have the unit meter, and meter divided by meter gives 1. This means that this term is dimensionless. That's a very important point. The relative change in length has no unit. Therefore, for E, only the expression from the numerator remains. Now we insert the units. 1 Newton corresponds to kilogram times meter per second squared. We divide this by square meters. 1 meter cancels out. What remains is kilogram per meter and per second squared. Now we write this as a dimension. Kilogram belongs to mass, m, meter belongs to length, l, second belongs to time, t, so we obtain m times l to the power of minus 1 times t to the power of minus 2. That is the required dimension. We write the dimension of E is mml to the power of minus 1, t to the power of minus 2. This corresponds to answer A. Finally, an important note. In physics, dimensions are treated like numbers. You can cancel them, compare them, and transform them. This allows you to check whether an equation is physically meaningful. Good luck, and see you next time.